structures, in particular A infinity algebras and their morphisms. And as you perhaps know, they generalize DG algebras and their morphisms as introduced yesterday by Professor Chen. And the plan is as follows. There will be 3 parts. A first part on A infinity algebras, first a bit of motivation, then the definition and some examples obtained from Hochschild cohomology. Then in the second part, I will state Kadeshvili's theorem on minimal models, and I will introduce morphisms of A infinity algebras and also A infinity categories and functors. And then in the third section, I will reformulate the definitions of A infinity algebras and their morphisms using the bar construction. I will look at A infinity modules and the derived category, and I think time will not allow to look at twisted objects. Yes, sorry, I have to delete this point. So let us start with a bit of motivation. A infinity algebras appear in several subjects. Maybe the most, the oldest occurrence of A infinity algebras, apart from topology, is symplectic geometry, where they appear in mirror symmetry, namely the so-called A side of mirror symmetry is given by Fukaya categories of symplectic varieties, and Fukaya categories are A infinity categories. If you want to learn more about this, you can look, for example, at James Pascalev's lectures at the Hausdorff Winter School in 2020. You can find it on YouTube. Then another important occurrence of A infinity structures is in the link between DG categories and infinity categories, where here by an infinity category I mean a quasi-category in the sense of Royal, Lurie, and many others. There is the so-called DG nerve functor, which to each DG category associates an infinity category, which is just a simplicial set with certain properties. And to define this infinity functor, this DG nerve functor, one looks at A infinity functor categories. Then a third occurrence, A infinity functor categories are used to describe certain homotopy categories, which will be important in Xiaohua Chen's lectures tomorrow. Namely, he will need to consider the homotopy category of homotopy short exact sequences in a DG category, for example, in an exact DG category. And then finally, let me not omit motivations which come from classical representation theory. Let me state 2 problems which appear in classical representation theory and where A infinity structures are helpful. For this, let me fix a field K, and let's look at an associative unital K algebra. It can be finite or infinite dimensional, and a complex of right modules over this algebra. Then we often form the homology of such a complex, just given by these subquotients of the components. These contain some information about the complex of A modules, but not all information. And well, if we just look at them as vector spaces, what we can ask, or if we look at them as A modules, we can ask what additional information is needed to reconstruct the complex up to quasi-isomorphism from its homology. Yes. So given its homology, what is the additional information needed to reconstruct the complex itself up to quasi-isomorphism? And here the answer is, well, this the homology of the complex carries a unique minimal A infinity module structure over the given algebra A, and this A infinity module structure encodes precisely the information which we need to reconstruct the complex from its homology. Now, another problem from classical representation theory is the study of modules with a filtration by a given subquotients belonging to a given family of modules. So we take B an algebra, and we take n B modules, and we look at the category of B modules having a finite filtration with subquotients among the MIs. So in other words, we look at the closure under iterated extensions of the set formed by these n modules. And it is clear that this category of iterated extensions is strongly related to the Yoneda algebra of the sum of the MIs, but it is not so clear how we can reconstruct it from the Yoneda algebra, and in general we cannot. However, this Yoneda algebra carries a canonical minimal A infinity algebra structure, which does encode the additional information we need. So we can endow this Yoneda algebra with higher multiplications so that it becomes an A infinity algebra. And this A infinity algebra contains all the information to reconstruct the category of filtered modules. And let me remark that this problem is closely related to the representation theory of boxes in the sense of the Kiev school. In particular, there is work by Ovsienko from 1997 and 2005. And this idea was successfully applied. The idea of representations of boxes and their link to A infinity theory was successfully applied by Stefan Koenig, Julian Kulshammer, and Ovsienko in 2013 to the study of quasi-hereditary algebras and their exact Borel subalgebras, in particular the problem of uniqueness of such exact Borel subalgebras. Okay, so I hope at least one of these motivations will have motivated or everyone in the audience. So now let me come to the definition of A infinity algebras. The notion originally comes from topology, from the work of Stashev, as he was interested in group-like spaces endowed with a multiplication which is well defined up to homotopy and associative up to homotopy. For example, loop spaces of loops in a topological space. And in order to study these, he invented first A infinity spaces and then A infinity algebras. A infinity algebras appear when we look at cellular complexes associated with A infinity spaces. Here you see a picture of Stashev. This must be from the 60s, I suppose, when he made this invention. And well, he is now 87 and still often goes to lectures, in particular online lectures. Here you can see him in 2020. Okay, now to give you the formal definition, let me fix a field K. Some things can also be developed over a commutative ground field, but since I don't have much time, let me just stick with the case of a field. And let me introduce a bit of notation. I will denote by GK the category of graded, Z-graded vector spaces. Just a moment, I have problems with my pointer. Yes, okay, now it works. The category of Z-graded vector spaces. And in this category, the morphisms which we consider are homogeneous morphisms, but of arbitrary degree. Okay, and this category is endowed with a tensor product given in the usual way. The nth component of the tensor product is the sum over p plus q equals n of vp tensor wq. This is the definition of the tensor product at the level of objects. And then we also have a tensor product defined at the level of morphisms, namely the tensor product of two morphisms f and g, whose degree is denoted by the absolute value. We define the tensor product of the two morphisms by this formula. When we evaluate the tensor product of morphisms, then, as you can see, we have to switch the position of G and V. Yes, on the left and on the right, the position of G and V is switched. And then we have to use the causal sign rule whenever we switch two symbols of degree P and Q. We have to insert a sign -1 to the P times Q. And so this is very important. Yes, so, so in the sequel, I will often write tensor products of morphisms, and additional signs appear when you apply these tensor products to tensors. And well, fortunately, this allows to get rid of these additional signs. So we get a few signs less with thanks to this rule. Okay, then we also have in this category, we have an internal HOM. So HOM is again a graded vector space, and the nth component of this graded vector space is given by the homogeneous morphisms of degree n from V to W. Now, starting from this category of graded vector spaces, we form the category of complexes. As usual, a complex is a graded vector space together with an endomorphism inside this category, endomorphism of degree +1 and whose square vanishes. And we have morphisms. Morphisms in this category are always of degree 0 and commute with the differential. And the category inherits a tensor product. And here you see a first instance of the use of the causal sign rule. Yes, the differential of the tensor product just appears like this without any signs. The signs appear when we apply these formulas to elements. And again, we have an internal HOM, and the differential now is the graded commutator with the differentials of V and W. And we have the shift or suspension functor, which shifts degrees by +1 and changes the sign of the differential. And finally, we have the homotopy category, which has the same objects as the category of complexes, and where morphisms are given by homotopy classes of morphisms of complexes. So we go modulo this subspace where H runs through all homogeneous morphisms of degree -1 from V to W. So this is just H0 of the morphism complex. And more generally, if we look at Hn of the morphism complexes, we get morphisms in the homotopy category from V to the nth suspension of W. Okay, and now with these notations, I can state the definition of an A-infinity algebra. It's a Z-graded vector space endowed with graded maps, so homogeneous Kähler maps, Mn, from the nth tensor power, in the sense which I have just defined, of A to A. They are defined for n greater or equal to 1, and they are homogeneous of degree 2 minus n, and satisfy an infinite system of quadratic equations. Namely, the first one is that M1 composed with M1 vanishes. So in other words, M1 is the differential of a complex. So A endowed with M1 is a complex. Then the second one can be written like this. If we compose M2 with M1, then that's equal to M2 composed with this sum. And well, here you recognize the differential of the tensor product of two copies of A. So this rule just says that M2 is a morphism of complexes from the second tensor power of A to A. M2 is a morphism of complexes. And well, equivalently, one can also say that M1 is a graded derivation of degree +1 with respect to M2. Okay, then the third quadratic equality links M2 and M3. We can write it like this. So here on the left-hand side, you recognize the associator for M2. If we evaluate this on 3 elements, say of degree 0, to simplify matters, then we get this difference, yes, which is the associator for M2. And on the right-hand side, well, as you can see here, we take M3 and we take its commutator with the differential. Yes, this is the differential of the third tensor power. This is the differential of A. And this is the graded commutator between M3 and these differentials. So what we see here on the right-hand side is the boundary of M3 and the morphism complex from the third tensor power of A to A. And so in other words, this means in particular that this associator is 0 up to a homotopy given by M3. Yes. And so M2 is a morphism of complexes, which is associative up to a given homotopy given by M3. Okay. And well, the next, here's also the next equation in this series. Yes, so here on the left-hand side, you can see a higher commutator, if you like. Yes, you form the commutator between M3 and associator, higher associator. Associator between M3 and M2. Yes, we have M3, and we multiply 2 of the arguments together in all possible ways. And here on the left, we take M2 and we multiply 3 of the arguments together in all possible ways. And we throw in suitable signs. And this is the higher associator, and it should also be homotopic to 0. It should be the boundary of a given homotopy M4. And the general equation in this series, in this system, infinite system of equations, is this one. So on the left-hand side, we have a higher associator. And on the right-hand side, we have the boundary of Mn. Boundary in the morphism complex, and here a higher associator. Yes, we have, in total, we have n arguments. we multiply some of them together, and then we multiply the result. We throw in suitable signs that gives us the higher associator, and it should be homotopic to 0 by the homotopy given by mn. Yes, so in pictures, here we have our n arguments, a1 up to mn. We multiply some of them together by ms, and we get a new string of arguments, and we multiply these together. All of them are multiplied together. We throw in suitable signs and take the sum over all possibilities of doing this, and that should give 0. So here I have moved this term to the left in this formula. Yes, 0 on the right, so I've moved this differential also to the left. And well, yeah, this notation with the little segments has the advantage of giving few things to draw. If you're ready to draw a little more strokes, then you can draw using trees. Yes, so we view the mi's as operations with n inputs and 1 output. So we have our n arguments. We multiply some of them together using ms, and then we leave the others alone, and we multiply the result of ms together with the others using mu. And again, we have suitable signs, and the sum over all possibilities gives us 0. Okay, and now some consequences of the definitions. Well, so first of all, the algebra A with M2 is not an associative algebra in general, but the homology of A becomes an associative graded algebra for the multiplication induced by M2. Then secondly, well, if our algebra is concentrated in degree 0 by chance, then it is an associative algebra for M2 because the MNs vanish simply for degree reason. Yes, in degree 1 it is of degree +1, so that takes us out of degree 0. In degree 2 it is the multiplication M2. In degree 3 it is of degree -1, which again takes us out of degree 0, etc. And so all the MNs except M2 vanish, so that we get an associative algebra. And also, if it's not necessarily concentrated in degree 0, but all the MNs for n greater or equal 3 vanish, then the axioms say precisely that A endowed with M1 and M2 should be an associative differential graded algebra in the sense of Professor Chen's lectures yesterday. And conversely, whenever we have a DG algebra, it can be considered as an A infinity algebra with vanishing MNs for n greater or equal to 3. And here, notice that I have not spoken about unitality. I have not mentioned units. There are various possibilities of introducing units. We can introduce strict units or homological units. I will say a little bit about this later, but it's something which should not worry you. It is well understood what goes on with units. Okay, so let me give the first examples of possibly non-trivial A infinity structures, more general than where we have non-vanishing higher multiplications. For this, let's take B, an ordinary associative algebra concentrated in degree 0. Let's fix an integer greater or equal to n. And what we will do is we will deform this algebra. We will consider first order deformations of this algebra given by Hochschild cochains, respectively cocycles. So, okay, so we have fixed our integer. Now we choose an indeterminate epsilon of degree 2 minus n, whose square should vanish. Yes, we just take a graded version of the dual numbers over k, and we fix a linear map with n inputs and one output in B. So in other words, a Hochschild cochain and Hochschild n cochain. And now we consider the algebra A, whose underlying vector space is just a tensor product of B with this algebra of dual numbers, graded in a non-trivial way. And we endow it with vanishing M1 with the M2, which is the natural multiplication of the tensor product. Then we define ML to vanish for all L different from 2 and n. And we define Mn using this composition. Yes, so yes, remember A is this tensor product. So to define Mn, we take this tensor product and we project onto the nth tensor power of B. We set epsilon equal to 0. That gives us a map from A tensor n to B tensor n. Then for B tensor n, we apply the cochain C to these n arguments and multiply the result by epsilon to end up here in B tensor k epsilon. And that is, of course, a subspace inside A. And this composition is, by definition, Mn. Okay. And then, if you like, as an exercise, you can show that this construction of A together with the MLs yields an A infinity algebra if and only if our Hochschild n cochain is in fact a Hochschild n cocycle. It's differential, it's Hochschild differential vanishes. Yes, here I have written down the Hochschild differential. And well, you will, yes, this already looks very similar to the conditions which define an A infinity algebra. And in fact, we have this equivalence. And so this means, if you like, that Hochschild n cocycles always determine first order deformations of a given algebra in the realm of A infinity algebras. Okay. Yes, so far for the definition and the first examples. Now, let me come to minimal models. Minimal models will yield a lot more examples. So again, let me take for B an ordinary associative unital algebra and M some B module, as we have seen in problem 2 or problem 1. Yeah, well, actually in both problems we have seen such a module. And the claim is that the Yoneda algebra of this B module has a canonical A infinity structure whose M1, whose differential M1 vanishes, and whose M2 is the Yoneda product on this Xed algebra. Okay, now to get this structure, well, we proceed as we would proceed in order to compute the Xed algebra together with the Yoneda product. So we choose a projective resolution of M, in other words, a quasi-isomorphism between a complex, right-bounded complex with projective components and the complex M concentrated in degree 0. And we look at the endomorphism DG algebra of this complex of projective models. The endomorphism DG algebra introduced by Professor Chen yesterday. So its nth component consists of the graded endomorphisms of P of degree n. Yes, so this is also in conformity with the notations which I introduced at the beginning. The multiplication in this DG endomorphism algebra is simply given by the composition of graded endomorphisms. And well, this is a differential graded algebra, and thus an A-infinity algebra. And of course, as you know, the homology of this differential graded algebra gives us the Yoneda algebra. This is one way of computing the Yoneda algebra with its product induced by composition of graded endomorphisms of the projective resolution. And now, well, there is a general theorem which tells us that if we have some A-infinity algebra A, then on its homology, we also have a canonical A-infinity algebra structure with vanishing differential. This is Kadeshvili's theorem from 82. We take an A-infinity algebra. We look at its homology for M1, for the differential M1. And then the claim is that this has an A-infinity algebra structure such that M1 vanishes. Yes, it's the natural M1 on homology. The natural M1 on homology is the vanishing differential. M2 is induced by the M2 of A. So in this example, it would be induced by the composition of graded endomorphisms. So here it is the Yoneda product. And so this is the first condition which we have. And then the second condition is that we should have a quasi-isomorphism of A-infinity algebras between the homology of A endowed with this A-infinity algebra structure and A itself. And this quasi-isomorphism should become the identity in homology. So it should lift the identity of homology. If we take homology on both sides here, yes, on the left we have the zero differential, so homology is H star A itself. On the right-hand side we have H star A, and phi should induce the identity between these two copies of H star A. Okay. I have not yet defined what a quasi-isomorphism of A-infinity algebras is, but I will do it in a few minutes. And yes, so I said, I mentioned canonical structure. It is actually not so canonical, this A-infinity algebra structure. It is unique up to a non-unique isomorphism of A-infinity algebras. So if we have two such structures on H star A, they are related by an isomorphism of A-infinity algebras. Now, an isomorphism of A-infinity algebras is not just a linear isomorphism which commutes with all the structure. It is something much more complicated. It has higher components. So this equivalence relation is a highly non-trivial equivalence relation, and in particular the MIs for this structure are not unique as linear maps, not at all. Yes, although the collection of all these maps is unique up to non-unique isomorphism of A-infinity algebras. Okay, so as I said, these non-trivial notions of A-infinity morphism and A-infinity quasi-isomorphism will be defined in a few minutes. And let me introduce a bit of terminology. We say that an A-infinity algebra is minimal if its differential vanishes. Yes, so what we construct here is a minimal A-infinity algebra structure. A infinity quasi-isomorphic to the given A infinity structure on A. And in this situation, we call H star A with its A infinity structure a minimal model for A. So in small examples, one can compute this completely explicitly. Suppose that we are given an algebra B by a quiver with relations. So we take this A4 quiver and we require this relation. For M, we take the sum of the 4 simple modules associated with the vertices. And then it is not hard to compute that the Yoneda algebra in this case can be described by this quiver. Yes, we revert the arrows in degree 0 give rise to extensions in between the simples. Elements of degree +1. Yes, I look at right modules. And then we have this relation which gives rise to an element in x2 from x2 of S4 by S1. And well, you can compute that the composition of any 2 consecutive extensions vanishes, and that M3 of these 3 extension x1s is non-trivial and equal to E in one choice of minimal A infinity structure. Yes. Okay. Well, so one can construct these minimal models inductively, or one can construct them using so-called homological perturbation theory. I don't have time to give you the details, but you can find them in the appendix to the notes. At the end of the notes, there's an appendix which explains homological perturbation theory applied to this problem. It's very nice. There's a nice algorithm due to Merkulov and explained, for example, by Kontsevich and Sabuman. Okay. And then, well, of course, it is nice if the higher MNs can be chosen to vanish. Yes, we say that the A infinity algebra A is formal if we can find a minimal model where the higher MNs vanish. Yes, so even the vanishing of the higher MNs is not something independent of the choice of minimal models. There can be minimal models with vanishing higher MNs and A infinity isomorphic minimal models with non-vanishing higher MNs. But if we can find a minimal model where they vanish, then we say that the A infinity algebra is formal, and that's of course a desirable property. And sometimes for a graded algebra, one can show that all A infinity algebras A with homology B are formal. Yes. And in this case, this graded algebra is called intrinsically formal. Yes, so a graded algebra is intrinsically formal if we cannot endow it with a higher structure where necessarily some MNs are non-zero. Okay, and there's a criterion for intrinsic formality due to Seidel and Thomas from 2001. Yes, in terms of Hochschild cohomology, if these bigraded Hochschild cohomology groups vanish for a graded algebra B, then this is sufficient for the algebra to be intrinsically formal. Okay, so this is of course very nice. When we have an intrinsically formal algebra, then in order to know that A is formal, we just have to look at its homology as a graded algebra. Okay. And well, in practice, one also encounters non-formal algebras in many situations. And it's a sufficient condition for non-formality of a DG algebra is that there are non-vanishing messy products. What is a messy product? Let us take three homogeneous elements, U, V, and W. Yes, we can view them, if you like, as morphisms from the free model of rank 1 to itself. And then we suppose that UV is homotopic to 0 by an element little a, and that VW is also homotopic to 0. It's the co-boundary of an element little b. And so if we look at the composition of the three of them, then in homology, this composition vanishes for two reasons. The first reason being the existence of A, and the second reason being the existence of B. And then the difference, essentially, of these two reasons becomes a co-cycle, and so defines a class in homology, which of course depends on the choices which we made, yes, on the choice of A and on the choice of B, and on the choice of U, V, and W in their homology classes. So this element, this difference, lives in a certain quotient. But this element inside this quotient always equals the element of M3 applied to UV, to the classes UV and W, and this for any choice of minimal model. Yes, so we have something which is independent of the choice of minimal model, and therefore, if the algebra A is if this does not vanish, then M3 will not vanish for any choice of minimal model, and so the algebra is not going to be formal. Okay. And now, yes, as promised, let me come to the definition of morphisms of A-infinity algebras, as we have already used them in the statement of Kardashvili's theorem. Okay, let's take A and B two A-infinity algebras. Then a morphism of A-infinity algebras is a family of graded maps. So family defined for n greater or equal to 1. So of degree 1 minus n. So in particular for n equals to 1, we just get an ordinary map of degree 0 between these two graded spaces. And this map F1 of degree 0 should commute with M1, so it should be a morphism of complexes. And then if we compose F1 with M2, we should find the same thing as M2 composed with F1 tensor F1, yes, which means that F1 is a morphism of algebras up to some correction term, and this correction term is the boundary of F2 in the morphism complex. And so F1 commutes with multiplication up to a given homotopy given by this F2 of degree minus 1. Okay. And then more generally, we have this rule for the higher terms. Yes, so it is actually not so complicated, except perhaps for the signs. If we view it again in a picture, so on the left-hand side, what do? We have our n arguments. We multiply some of them together. We get a new string of arguments, and we apply the morphism fu to this string of arguments. And this should be the same thing as if we apply the fi's to all the arguments, and then we multiply the new string of arguments together using MR. Okay. Yes, so this is the notion of morphism. So again, you can see it is a non-trivial notion. Somehow the main part is the F1, which is of degree 0 and which will induce an algebra morphism in homology. And the higher structure is encoded in the F2s, F3, etc., which measure the deviation of the successive fi's to verify a commutation with multiplication. Okay. And then we say that such a morphism is a quasi-isomorphism if F1 is a quasi-isomorphism of the associated complexes. We say that the morphism is strict if all the higher fi's vanish. So this would be the naive notion of morphism. It's something, a linear map, which commutes with all the data. And then we have the identity morphism, which is the strict morphism whose F1 component is the identity. And we have a natural formula for composition. And we will see, for example, so now in Kardashvili's theorem, we have seen that each DG algebra is A infinity quasi-isomorphic to a minimal A infinity algebra. And somehow conversely, one can also show that each A infinity algebra is A infinity quasi-isomorphic to a DG algebra. If you like a kind of, this will be quite a big DG algebra, yes. So on the one hand, for a given A infinity algebra, we have a minimal model with vanishing differential and the smallest possible components, yes, or the components are equal to the homology, so they are the smallest possible in the quasi-isomorphism class. That's the minimal model. And then, if you like, we have a kind of maximal model where we will have very large components, but we will only have M1 and M2, no higher operations. We will have a true differential graded algebra. And yes, so in particular, this also shows that, if you like, from the point of view of quasi-isomorphisms, A infinity, the class of A infinity algebras is not essentially bigger than the class of DG algebras. Yes, we can up to quasi-isomorphism, they are the same. But we will see that A infinity algebras have a lot of nice properties which DG algebras do not have, and similarly for their models. And let me stop here for the first part of the lectures. Thank you very much.
Thank you, Bernhard, for a nice talk. Are there any questions, comments? There is a question in chat, Bernhard.
Is there a question in the chat?
In the chat.
Moment. Yes. Question in the chat. You mentioned that AM2 is not an associative algebra in general, yes. But if we view AM1 as a complex in the homotopy category and equipped with the multiplication map M2, is it true that AM1 is indeed an algebra object in the homotopy category? Yes, absolutely. That is true. It's an associative algebra object in the homotopy category. Yes. Up to homotopy, M2 is associative, and the homotopy is given by M3. Absolutely, yes. And yes, of course, one can also ask whether, given an algebra in the homotopy category, we can find an A infinity algebra which it comes from, and I don't have a counterexample off my head, but I'm sure that this is not the case.
Are there any questions on this? And I have also one question, Bernard. And which properties of associative algebra is it transferred to the A infinity? I mean, if we have
Sorry?
if we have an associative algebra,
Yes.
and we construct the A infinity algebra, I mean, if it is possible, such that its homology is just this associative algebra.
Sorry, I did not understand everything. The sound on my side is not so good. So we take a graded algebra, right? And we want
Yes.
to find...
and assume that there exists the A infinity algebra such that the homology of this A infinity is equal to this algebra.
Right.
And which properties of this algebra can be transferred to the A infinity? I mean, is it possible to use this A infinity algebra for studying some properties of this algebra?
I see. So you would, I see. So one could say that your question is, given an A infinity algebra, if we know its homology, what can we infer about the A infinity algebra itself? Could one reformulate the question like that?
Yes, but I mean, I want to study this algebra, not A infinity, but by using the A infinity.
You want to study this algebra, not the A infinity algebra. Yes. Yes, that's not so obvious. I mean, if you like, we can view the A infinity algebra. The A infinity algebra structure can be viewed as a deformation of its homology, and so the question amounts to asking, if we know a deformation of our algebra, what can we infer about the algebra itself? So in other words, the algebra itself, it's a degeneration of its homology, and sorry, of the infinity algebra. And so the question is related to the question of which properties are preserved under degeneration. Yes. And yes, and I don't know any general results on this question. It will very much depend on the particular situation, I think.
Thank you.
Yeah. And then there is another question by Edmund. Just to reconfirm, he said that there are examples of algebra objects here. Yes, I think so. Yes. I'm sure there are such examples. Yes. Yeah, examples of algebras in the homotopy category which do not come from A infinity algebras. Yes.
Next, there's another question.
I mean, this is again related to a problem from deformation theory. Yes, usually there are nth order deformations which cannot be extended to higher order deformations, and this is related to the question. Yes.
So, are there any more questions? Okay, so thank you, Bernhard, again. And we will start, I think.